So let's take that as the reference. So we started and split it up. Time for a quiz, right? No? Anyway, so keep in mind that if there were to be a quiz, it'll always be at the beginning of the class. Okay, so this slide kind of summarizes what we discussed most of last lecture, discussing the way discussing the stack smashing attack, the defenses that have been proposed, and how some of the defenses can be overcome by the attackers, and then how the defense can be improved, and so on. Yes.
Possibly, could you switch the slide or where's the
So that's not going to work because I need to use the board too. So let's, if it's completely invisible, then I'll do that. Okay. So tell me if it is manageable or unmanageable. Then I'll have to just switch it on and off. That's okay. So so we talked about stack smashing and the defenses. Then we started talking about protection against injected code, right? So because most of the time when the attacker does a control flow hijack, they want to execute their own code. Okay, so that's code injection. And in order for code injection to work, a requirement is that the data sections be executable, right? Because whatever, again, always keep in mind, we are talking about vulnerabilities in programs, which means that to start with, the attacker has no control over the target system, right? So the target system is running some piece of benign software. The software may have vulnerabilities, but it's not attacker's code. So what happens is that the attacker has to first, originally the benign program is doing what it is, presumably meant to do, and somehow the attacker has to use this benign behavior to somehow subvert the execution, right? So as part of this benign behavior, this application can read data, and this data could be coming from the attacker because, again, serving the attacker, even or serving an untrusted user is typically the role of these programs. So when that data is read, the data is going to be in writable memory, right? So if the attacker wants to use that as code, then the attacker also needs to execute permission on that piece of memory, right? So what the about 15, 16 years ago, processors, specifically Intel processors, didn't have this ability to distinguish between writable and executable, right? So anything writable was once you have read, I'm sorry. So it's typically the case that things that were writable was also left executable, right? And people figured out that, okay, this is a big problem. So both the processor developers as well as the operating system vendors came out with this data execution prevention, as it is called, or sometimes it's also called write XOR execute, which basically means that either you can have the write permission or you can have the execute permission, but you cannot have both, right? So, so what happens is that from then on, all the code has only read and execute permission, and all the data has read and write permission, right? So this way, whatever is data cannot be executed, and whatever is code cannot be written, right? So this way, you prevent the attacker from writing code into the code sections. You also prevent the attacker from interpreting the contents of data as code. Okay, so that's the DEP, and it got implemented and deployed pretty quickly, right? So by maybe 2006, most systems were using this feature, and at that point it became impossible to do code injection. And so the attackers said, okay, if I don't inject code, what can I do? So you have this notion of code reuse attacks. Okay, so that's really what we are going to talk about for some time. So there are many forms of code reuse, and we will talk about them one by one. So the first one is what is called return to libc. And libc is the standard system library. Okay, so the one that implements all the system calls and a whole lot of functions like formatted print and reading and so on. Right? So most of your input output that is in this C library. Okay. Now, although it's called return to libc, there's nothing special about returning to this library. What it says is that you return to instead of calling a function, you can also make the function execute by returning to the beginning of the function, right? Because all that matters to a function is, you start executing it from the beginning, right? So it doesn't matter how you got transferred to the beginning of the function. So you could as well do a return, okay? So what the attacker does is typically the typical target could be like the system function that we mentioned before, okay, which allows the attacker to execute a shell command. So the typical way this type of thing works, again, let's draw our stack layout. Okay, so typically that is return address, and then base pointer, and so on. Okay, so let us talk about so what the attacker does in this case, let's say that once again the attacker is using a stack buffer overflow, and they're able to overwrite the return address. Okay, so what the attacker does is they are going to write the address of system function. Okay, so this is a function inside the C library. So the attacker, as we have said before, in order to do these exploits, the attacker has to know exactly where things are. So they need to know where is this function. So they are going to override this with that information. Okay. So now what happens is that the execution is going to now start at the beginning of the system function. Okay? Now, what the system function is going to do is it's going to think, hey, this is a legitimate call. Therefore, the caller gave me the information that I need in the way that I usually expect, right? Which means that it expects some return address here. It's going to expect some argument 1 here, argument 2 here, and so on. Okay? Because once you return with the stack pointer pointing to over here, right? What the call function is going to think is that, okay, wherever the stack pointer is pointing, one step above that is the return address. Then I'm going to have arguments and so on. Okay. So notice that if the attacker has a buffer overflow and they override the return address, they can also overwrite all of this, right? So the buffer overflow overwrites all of that, which means that the attacker controls all of this data, right? Which means that the attacker is able to control this data. What the attacker writes over here is going to be interpreted as the return address by system function, and that itself is not that interesting, right? What the attacker wants to do is that if it's a system function, they want to pass in the name of a command that they want to run, right? So that will be in argument 1. Right? So what the attacker wants to do is basically, by controlling the arguments of the system function, they can pretty much execute whatever command that they want. Right? So this is an example of what is called a return to libc attack. Right? And what it means, the main point of a return to libc is what? Why does the attacker execute return to libc? Someone can lift their, yeah, go ahead.
To execute malicious code.
True, but again, why do they do that? Right. So the main point being that, once again, I'm sometimes I ask you questions, and sometimes they require thinking. Sometimes they just require. I'm just emphasizing a point that should already be obvious, such as not having to inject code. Right. So in this case, return to libc is used because the attacker simply wants to reuse existing code. Right? So that is your return to libc. Now, it's not that easy in many cases. For instance, even if it is the calling of a system function, the first argument to system function is a string, right? And a string in C is passed as a pointer, right? So what the attacker needs to include here is a pointer to command name, right? So this means that the attacker has to put the command somewhere else over there and store a pointer to that over here, right? This means that the attacker has to sort of figure out, more about the exact layout of the program, right? And that means, more work for the attacker, right? So, and sometimes it may be difficult because the buffer overflow itself may happen because of, let's say, a string copy operation. Okay? If it is a string copy operation that causes a buffer overflow, then that limits the attacker, right? So how does it limit the attacker? What is the limitation of string data in C? Yeah.
Immutable.
No. String data in C is not immutable. What? It is null terminated. Therefore, it cannot have embedded nulls. Right? So, since it cannot have embedded nulls, that means that if the attacker wants to override, they can never include a single null byte in this. Okay, and that of course is a limitation because often pointers may have some one of the bytes being null, right? Because of how the layout is. It's possible that the pointers may have a null in them, and if that is the case, then the attacker may not be able to make this pointer point to the data that they want, because this pointer, in order for it to be valid, may need a null character to be in there. So in general, what happens is that depending upon how the vulnerability is, the attacker has certain constraints that they need to deal with, which may make the attack, which may conceptually seem easy, to be actually somewhat hard. Yeah.
I was gonna ask, why not store the string before the return address then? Because if you know the size of the local variables and you're already doing the buffer overflow to do this attack, why not just store it before instead of after? Because you're doing a pointer.
No, it doesn't really matter where it is, right? But no matter where it is, you have to put a pointer to that over here, right? So you still need to know where that data is going to be, right? So suppose you have a buffer overflow from here, right? The attacker only needs to know, in order to override the return address, they need to know this distance, right? And this distance is fixed given the function, okay? But the exact location, right, of the return address is not necessarily fixed, right? Because the stack could be anywhere, right? And so anytime the attacker has to find out exactly the location of something, that requires some extra work. And so of course the attacker would like to do the least amount of work to get their attack going. Yeah, is that a question? Okay, so in practice there are limitations that may make this sort of return to libc to be not so useful. Okay, so attackers came up with a second approach, which is called the return-oriented programming, or ROP. Like return to libc, this attack also works by returning, right? So instead of trying to inject code, it doesn't inject code. It tries to return to some part of the existing code. Okay, but the difference is that with return to libc, the typical goal with return to libc is to execute some powerful function. Okay, like system. The attacker may not be able to do that either because in the target program there are no powerful functions that the attacker can use. Okay, or there may be problems like, okay, there are pointer arguments that they are not able to provide. So instead they may be looking for, another approach where they don't have to use an existing function, but instead they can stitch together small snippets of code, right? Each of these snippets themselves may not do much, but by stitching them together, the attacker can basically achieve arbitrary computation. Right? So essentially, this gives the attacker the ability to the same capability they can have with injected code, because injected code means it's attacker's code, so the attacker can do anything they want. So they can achieve the same goal with ROP, except that they really don't have to inject anything at all. And so they don't have to defeat this DEP, right? The DEP mechanism they don't have to defeat. They can work with existing operating systems and so on, and still execute arbitrary code. So let's see how this works. Okay? So I'm going to show you an example, and the goal of this example is to execute a system call. Okay? So this program wants to the attacker wants to execute a system call, and for instance, one system call could be to execute a shell, right? But a more common target is to change the memory protection, okay? Because even though by default the program is configured so that the data is not executable and code is not writable, right? This is a default. But there is this system call called mprotect, right? So programs can use the system call to change permissions of memory whatever way they want, right? So they can definitely create memory region that is both writable and executable. Or they can take a region that was previously writable and just turn it to be executable and non-writable, right? So whatever permission they want, they can do it. So a typical attacker goal these days is to execute an ROP attack, to the purpose of which is to do an mprotect, right? So what the attacker does is they first inject code using a buffer overflow, right? So same way as before. The next thing they do is that they start a ROP attack. The purpose of the ROP attack is to change the permission, say in the stack region, so that it becomes executable, right? And after that, they can simply start executing their own code, right? Because they've already, using the buffer overflow, they have put the code on the stack, right? Except that right now, they cannot execute it because the stack has no execute permission. So what they do now is they execute this ROP exploit, also called an ROP chain. And the purpose of the ROP chain is to simply change the memory protection on the stack so that it is executable, okay? And once it becomes executable, now their code is executable, so they can just jump to that code, right? So this is sort of how ROP is used in the real world, and we'll show how in this particular case